Good morning, all of you. Any questions from yesterday's class? And if not, let's get started. And all of you need to look at IS 10262. So I'll go through the illustrative examples, example which is given in IS 10262. And one example I'll go through thoroughly. Second example, you can go through it yourself, and an assignment will be given. You need to repeat the assignment with whatever illustrative example that is given in the code, that is for M40, and you need to repeat this assignment for M35. Okay. Anyway, with that, let me start. I don't know why student strength is less today, because this today class is very important. So this is the example, illustrative example that is given in IS 10262. Mixed proportioning for concrete of M40 grade. What I suggest is, if you have some notebook or something like that, you just at least make a note of it, okay? So that when you are following lecture, you may not be able to flip over the code book. And key points you can note down, and afterwards you can go through the code book. So grade designation. So we are noting down all the information that is required for design mix calculations here. Stipulations for proportion, grade designation, M40, type of cement, OPC 43 grade conforming to IS 8112, maximum nominal size of aggregate 20 mm. Please note that in IS 10262 we have 3 tables. Table 1 gives you standard deviation for getting the target strength, and table 2 is actually going to give you this let me show you that water content, maximum water content, and that is based on the assumption, or this table is actually made for certain nominal maximum size of aggregate. This is let me just table 2 is for angular coarse aggregate. Sorry, table 2 is for angular coarse aggregate and slump between 25 to 50 mm. Okay. And table 3 gives you volume of coarse aggregate with respect to the total volume of aggregate, and table 3 is given for assuming water cement ratio of 0.5. So anyway, to make use of these tables, we require this information. Any corrections that we require to apply. So that's why maximum nominal size of aggregate 20 mm is noted here. Even when you want to read from table 2, you require this information. What is the maximum nominal size of aggregate? What is the minimum cement content? That is also noted. 320 kg per meter cube. Maximum water cement ratio 0.45. Workability 100 mm. Slump. Please note that workability here is measured in terms of slump. And some other cases you may be using compacting factor or flow parameter or something like that. Okay. Slump is taken as 100 mm. And usually in this IS 10262, because table 2 is based on slump, we go with slump. Okay. And exposure condition is severe. And please note that more details about the mixed design you will be learning as part of your concrete technology course. Here we are trying to get an idea, a glimpse of it as a part of this design course. Okay. So exposure conditions severe, and this information is required for us to make use of IS 456 table 5. And method of concrete placing, pumping. And this information also will be using in this code IS 10262. Degree of supervision good, and that will be used when we are actually making use of table 1 of IS 10262. Type of aggregate, crushed angular aggregate, and table 2 is based on angular aggregate. So that point is noted here. Maximum cement content 450 kg per meter cube of concrete. And this, why this maximum ceiling is placed, will if our cement, whatever after calculations, whatever we get the cement content, if it exceeds this value, then we need to make some correction. Again, we need to do the design. Okay. Chemical admixture type, super plasticizer. This super plasticizer helps us to reduce the water content. We'll see that. Okay, so this is the information. So with this, we are going to start. So what is the first step? And from the above information, some more information is noted. Cement, same thing. Cement used is noted. And what is the specific gravity of cement? Specific gravity of the cement, actually you can get from manufacturer certificate, or you can assume some reasonable value, 3.15 specific gravity of cement. Chemical admixture, what kind of super plasticizer is that? That information is given here. Super plasticizer conforming to IS 9103. We already noted IS 9103 gives you the specifications for various admixtures. In the previous classes, we noted that. And what is the specific gravity of the coarse aggregate? What is the specific gravity of fine aggregate? Specific gravity of coarse aggregate, yesterday we noted it is varying from 2.5 to 2.7, something like that. Yesterday, in yesterday's lecture, we noted, and here it is taken as 2.74 for both coarse aggregate as well as fine aggregate. And also I emphasized yesterday all the saturated surface dry aggregate, that kind of thing is what is noted here. Water absorption, coarse aggregate it is 0.5%, fine aggregate it is 1%. Okay, so if the aggregate is not surface dry, fully saturated, then we need to make these corrections. Once we get a final water content, we need to make these corrections and then arrive at the actual water content. Okay, so whatever water content we are going to arrive is free water, and to that free water we need to apply these corrections, because this aggregate is going to absorb some water. That we'll see at the end. Okay. And what about the surface conditions? Free surface moisture. Coarse aggregate, it is dry in the sense coarse aggregate it is taken as nil here. Okay. And fine aggregate is nil. And also you can see here in brackets it is written absorbed moisture is also nil. Even though here water absorption for this particular aggregate is noted as 0.5% and fine aggregate as 1%, and here it is noted or it is assumed that aggregates are surface dry, and also they are not going to absorb any moisture. Okay, so whether they absorb moisture or not, it is immaterial. If they absorb moisture, we are going to apply correction, these corrections in the final water content. If they are not absorbing, then we'll ignore this information. Okay, any questions here? So now we need to here, if you see the point G here, sieve analysis, coarse aggregate and fine aggregate. So before we go in here, let me I think somebody is waiting or something. I will see that and then come back to you. Okay. So now let's go to this course aggregate. Okay. Course aggregate, what is this sieve analysis? Let me go to that section. Just read this one. 4.5. Course aggregate shall conform to IS 383. IS 383. Course aggregates of different sizes may be combined in suitable proportions so as to result in overall grading conforming to Table 2 of IS 383 for particular nominal maximum size of aggregate. Please read it once again. Course aggregates of different sizes may be combined in suitable proportions so as to result in an overall grading conforming to Table 2 of IS 383 for particular nominal maximum size of aggregate. This Table 2 of IS 383, it is actually giving you nominal maximum size of course aggregate. And let me show you once again that one, then you will get a better idea. So this is what Table 2 of IS 383. It is giving you nominal size of course aggregate. Nominal size of course aggregate. It is giving you based on the percentage passing for single sized aggregate, and this is percentage passing for graded aggregate of nominal size. So using this table, we'll get the nominal size of course aggregate. Before that, what this IS 10262 is saying is you can take course aggregate of different sizes and then combine them suitable proportions and then do the sieve analysis and then get the nominal maximum size of aggregate. Is it clear? Any questions here? So let me go to the table. In the example, let me go to this one here. So that is what is actually done here. Sieve sizes 20 mm, 10 mm, 4.75, 2.36. These sieves are used. And what IS 383 is saying, it is giving starting from 80 mm, 63 mm, 40 mm, 20 mm, 16, 12.5, 10, 4.75, 2.36. But in this, it is this 20 mm sieve is taken. You can see here 20 mm sieve is taken. In between 16 mm sieve and 12.5 mm sieve is not taken. Actually, you can see here. It is actually a dash is there. Okay, so there is no requirement that any amount can be passing through this. So percentage passing. Okay, so this can be skipped. 20, 10, 4.75, 2.36 sieves are taken, and then you can see this table here in the illustrative example. These sieves are taken. And then two types of course aggregates are taken. The first sample is denoted with this one, first sample, and second sample is 2. When first sample sieve analysis, 20 mm it is passing, 20 mm sieve, the entire aggregate is passing, and 10 mm 0 is passing, and subsequently all are zeros here. And another sample of course aggregate is chosen. Again, sieve analysis carried out, and this is the result. 100% is passing through 20 mm. 10 mm sieve size 71.2 is passing percent. 9.4% is passing through 4.75 mmC. Okay, so these two types of coarse aggregates are taken, and these two types are mixed together. And how much each percentage of each? Sample 1 60% is taken, sample 2 40% is taken. Okay, and these two are mixed, and that mixed aggregate sieve analysis result is given here. And now you see, what I suggest is, please, if you have notebook in front of you, if you have a notebook and or a pen and paper with you, you please note down this 20 mm and this number 100% passing, 10 mm sieve 28.5 passing, 4.75 mm sieve 3.7 is passing. You just note down this 20, 10, 4.75 and these numbers 100, 28.5, 3.7. You please note down those. Okay, so now let's go to, so now this combined aggregate, I want to know what whether it is complying with table 2 of IS 383 or not. Okay, table 2 of IS 383 or not. I want to see whether this is complying or not. So let me open this one. IS here. These are the columns which we need to look at. Percentage passing for graded aggregate. But because what we did is we took two different types of coarse aggregate and combined in 60-40% combination, and then that final coarse aggregate we did sieve analysis, and then we noted what is the percentage passing. So I just told you to note down against 20 mm sieve, what is the percent passing? 100 mm. Against 10 mm, what is the percentage passing? It is 28.5, which is actually falling between 25 and 55. And what is the percentage passing through 4.75 mm sieve? Here in the example, 3.7. 3.7 is lying in between 0 and 10. So the final combined aggregate nominal size, maximum nominal size can be taken as 20 mm. Is it clear? Any questions here under this coarse aggregate? Any questions? And please note that it is not necessary always you need to do this kind of taking two samples of coarse aggregate and combining them in certain proportions. Here it is 60-40, and it's not necessary to do all that. If you are able to find good coarse aggregate complying with the IS 383 table 2, you can use directly that one. But sometimes you may not have that kind of privilege. In that case, we are going to take two different types and then combine them and see how they are matching with the table 2 of IS 383. Is it clear? In this illustrated example, that is what is demonstrated, but it is not necessary that this combination is required. Okay, somebody has some question?
Sir, could you once again explain how did you confirm with the IS 383?
I told you have, please note that it's now we are in difficult situation and you should also cooperate, and you have pen and paper with you. Okay, so what I'm saying is you note down this 20, this is 20 mm sieve. You can see here IS sieve size 20 mm sieve. Okay, again is 20 mm, you note down 100.
Yes, sir, done.
And 10 mm you note down 28.5. And 4.75 again is that you note down 3.7 is passing. And 2.36 is nothing is passing. Okay, 0. 0 is not actually written here explicitly, but it is 0. So now you have 100, 28.5, 3.7. So now go to IS 383 table 2. First of all, we never used a sieve size greater than 20 mm. Okay. So hopefully we want to check whether whatever combination we did, it is going to match with the requirements of IS 383 table 2 corresponding to 20 mm. So now let's take this column 20 mm. And what is this column? Percentage passing for graded aggregate. So 20 mm, this is what it is saying. IS 383 is saying if you want to designate that particular course aggregate as 20 mm nominal size, it has to satisfy these requirements, these percentages. So in our case, what is the percentage passing through for sorry, here 20 mm. 20 mm, say what is the percentage passing? 100.
100%.
So 95 to 100, it is falling in that range. And the 16 mm, 12 mm is not required. Okay. And directly 10 mm. 10 mm, what is the percentage passing? It is 28.5. It is also falling between 25 and 55. And now what is the percentage passing through 4.75 C? 3.7. So that is also lying between the ranges which is given in IS 383 table 2. So that's why we are saying this particular combination or the final this graded aggregate, course aggregate, whatever we got, it is complying with nominal size of 20 mm course aggregate as per IS 383. Is it clear?
Yes, sir.
It's not necessary you need to do these combinations. That is also another thing that you need to keep in mind. If you want to do it, you can do it. Because you see, when you get a course aggregate and when you do sieve analysis, sometimes it may not be complying. It may not have all the particle sizes. Then it is better to have combination. So that is what is demonstrated in this example. Okay. Any other questions? So that is how we are saying here. Remarks, under remarks column, you note see here conforming to table 2 of IS 383. So we can say this course aggregate is of nominal size 20 mm. If we use this final, that means when we need to do this combination 60-40%, sample 1 60%, sample to 40%, we need to combine them, and the mixed one we need to use. Okay. If it is clear, let's go to the fine aggregate. Fine aggregate. Tell me, any question?
Sir, for which type of aggregate, sir? Sir, if the nominal size is same, suppose 20 mm, then sir, for which aggregate, graded or single size, the density will be more of?
Here we are grading, no? We are doing grading here.
Yes, sir, but if we have same nominal size, suppose 20
then
mm.
Then if you have a single size, you are not grading, you see the other column.
Okay, sir, but which one should we use for our in our concrete so that the density is higher, sir?
No, it doesn't matter. Whatever course aggregate you take, you do sieve analysis. And if you want to designate that as 20 mm, you need to have this. It should the percentages passing should comply with these ranges. If it is not complying with those ranges, you need to do some adjustment. That adjustment is nothing but what is shown here. You take different samples and combine them and make sure that final product is matching with the ranges that are given in IS 383.
So, sir, the density will be same for 20 mm single size aggregate and 20 mm grade aggregate.
What is that?
Sir, in concrete, the density will be same for 20 mm single size and 20 mm graded aggregate.
No. It's why density of concrete has to depend on the size of the aggregate. Density of concrete is it's a composite product which is coming out of fine aggregate, coarse aggregate, and then cement. So density of concrete is going to depend on overall density of all these aggregates, cement, and other things. Okay. Density of concrete is nothing to do with the size of the aggregate. size of the aggregate, we are making sure different sizes are available there, so that packing is proper.
Okay, sir.
Okay. Any other questions?
Okay, let me just reiterate at this stage. See, aggregates are natural products. They never come in one size. If you go to a quarry and take some stones, you will see that their sizes are varying. But then we do a sieve analysis to get an idea of how much is the variation. And then you adjust to make sure that you have a good gradation, so that finally the packing is better. Okay.
Okay. Any other question? Or we'll take more questions later. Okay. But I once again I'm telling you, please have pen and paper with you. And now let's see fine aggregate. Fine aggregate. Once you get aggregate to the site, you need to do sieve analysis, and then you need to compare whatever the outcome that you get from your sieve analysis with the ranges for different zones that are given in table 4 of IS383. Okay, and here this is an illustrative example here, that all that sieve analysis, everything is assumed to be carried out, and here the example is demonstrated taking that the fine aggregate is conforming to grading zone 1 of table 4 IS383. It is conforming to zone 1. If you recall, what is zone 1? Zone 1 is zone 1, actually we noted earlier, it results in harsh mix, something like that. Okay. And also zone 1 means zone 4 is finer. Finer in the sense, zone 4, let me open that. Maybe that makes you like understanding better. So this is what zone 1 to zone 4. Zone 1 you have bigger size particles more. Zone 4 you have smaller size particles more. Okay. Anyway, whatever sample that we have taken, we are assuming it to be zone 4. Okay, that's fine. If it is zone 2 or zone 3 or zone 4, whatever you get from sieve analysis, you take it. So it is zone 1 is assumed. Okay. So let's see what is the implication of this zone 1. It is actually going to be this information is going to be used in table 3 of IS 10262. Table 3 of this particular design mix code will be using this information. Okay, just keep a note of it, and then we'll proceed. So now we noted everything. We noted what is the data for all the materials, everything. Cement, we noted what is the specific gravity of cement, what kind of superplasticizer, what is the specific gravity of coarse aggregate, fine aggregate, and water absorption of coarse aggregate, fine aggregate, and whether they are surface dry or not. Okay, or free moisture. Free moisture in the sense, free moisture is showing us nil, means they are surface dry. Okay, and also we noted how to do how to find nominal size of coarse aggregate, and also how to get the grading zone of fine aggregate. So now let's start the next point. What is the target strength? First of all, what is the strength for which we are designing this mix? M40, 40 MPa. So FCK is for, yesterday I have given you this equation. Okay, I have shown you this equation. This FCK prime is target strength. FCK is the mix for which what grade you are designing, that is FCK. That is 40 MPa. And 1 plus 1.65. 1.65 is coming from definition of characteristic strength. Not more than 5% of the test results should fall below or 95% of the test result should be above the value. That kind of information. From there, this 1.65 is coming. And S is the standard deviation. S is standard deviation, where you are going to get this S from table 1 of this code. This code is 10262. Table 1 is giving you standard deviation. And to read that standard deviation, when you are reading that standard deviation, you need to know what grade of concrete you are trying to design. Here we are trying to design for M40. For M40, what is the standard deviation? That we can get it from table 1. But the table 1 of IS 10262 is based on certain assumptions. So there is a proper control on the site and other thing. Okay. So we need to make sure whether that proper control on the site is there or not. So let's see here in this initial information, starting information that is noted. Degree of supervision is good. So we are doing all these mixed design calculations, assuming that degree of supervision is good on the site. Okay. Accordingly, we are choosing standard deviation from table 1. Suppose you do these calculations and you deliver this concrete, or you do the concrete mix and then deliver it to the site. But in the site, whatever assumptions you made is totally different from what is the situation on the site. Then it may not result in whatever strength you wanted. Okay. Anyway, now S. All of you, please make a note of this on your paper. FCK prime is equal to FCK plus 1.65 S. FCK is 40 MPa. In this case, 1.65 is a number. S, we need to get it from table 1. We'll see there. Okay. And whatever I already explained, that is what is mentioned here. FCK prime is target average compressive strength at 28 days. FCK is characteristic compressive strength at 28 days. For M40, it is 40 MPa. S is the standard deviation. So now let's see, yes, what is S value? Here it is already, because the example is already worked out. Here it is saying from table 1, standard deviation is taken as 5 Newton per mm square. We'll see whether this is correct or not. Okay. So let's go to table 1. So table 1 of IS 10262 for M40. For M40, what is the standard deviation value? Assumed standard deviation. Code is giving some guideline to us. Code is saying you may use this standard deviation, 5 Newton per mm square. And but code is making, based on certain assumptions, code is prescribing that value. What is that? What are those assumptions that is given in this note? Yesterday we went through this note. Once again, let's go through it. The above values correspond to the site control having proper storage of cement, weigh batching of all the materials. This is very important. Whatever weigh batching, please note that volume, when you measure something in volume, the quantity is going to depend on how good is the packing. How good is the packing? And when you are filling some pebbles or something in a jar, the number of the quantity that goes into the jar depends on how you shake it. Shake it in the sense, when you vibrate it little bit after putting few pebbles, and you slightly shake it, and then it will those pebbles will adjust properly, and then you can put more pebbles. The simple experiment. Okay. So volume is going to depend on how good is your packing. That problem is not going to be there for weigh batching. So here this 5, whatever standard deviation that is specified by the code, that those are based on the site control having proper storage of cement. Okay, cement should be stored properly, in the sense if there is a possibility of moisture coming in contact with cement, it gets hardened, so cement becomes useless. So proper storage of cement, weigh batching, controlled addition of water, not indiscriminate addition of water, controlled addition of water, regular checking of all materials, aggregate grading and moisture content, and periodical checking of workability and strength. This is what, under these assumptions, this is the standard deviation that is specified. And if your actual site conditions are totally in violation of all these things, then you put some extra penalty. Penalty in the sense, your standard deviation is going to increase. How much it's going to increase? Where there is deviation from above, values given in the above table shall be increased by 1 Newton per mm square. Okay. Anyway, we started with the assumption that supervision is good. Degree of supervision is good. That's why we are assuming the site conditions are good. That's why from table 1, whatever standard deviation corresponding to M40, that is mentioned as 5 Newton per mm square, that is directly taken. If the supervision is not good, then we need to add +1. So 5 + 1, 6 is going to become. So now with all this, what is the target strength? 40 plus 1.65 multiplied by 5. So that is this value. So when we want to design for M40, we need to target this value, 48.25 Newton per mm square. Any questions here? Anyway, now so this is you can say this is a third step. Third step is getting the target strength. And fourth step is water cement ratio. Where do I get this water cement ratio? Water cement ratio, you can get some idea, because please note that this is all trial and error kind of things. We need to have some starting information. That information is already given in the beginning, stipulations. So using that information, you can go to IS 456 table 5. Yesterday we have seen that table 5 of IS 456 in detail. So table 5 of IS 456 is giving for different exposure conditions. What is the maximum cement ratio? Sorry, what is the maximum water cement ratio and minimum cement content? Table 5 of IS 456 is giving for different exposure conditions. What is the minimum cement content and what is the maximum water cement ratio? So here in the beginning, we noted what kind of exposure condition is this? We are actually the exposure condition, we assumed it to be severe, and we are doing all this mixed design for reinforced concrete. So that information is good enough for us to get an idea about water cement ratio. Okay, so let me open IS 456. IS 456 table 5, minimum cement content, maximum water cement ratio. And please note that read this title properly. The caption, you need to read it properly. Minimum cement content, maximum water cement ratio. Anyway, forget about minimum grade of concrete for different exposures with nominal weight, with normal weight aggregates of 20 mm nominal maximum size, 20 mm. So what is our coarse aggregate nominal size? It is 20 mm. Suppose our coarse aggregate nominal size is other than 20 mm, we need to apply corrections over this. That corrections are given in the earlier classes. I already told you corrections are given in table 6 of IS 456. Okay. Anyway, that correction in the current situation or the current example, whatever example that we are looking at, that correction is not required to be applied. So here, since our nominal maximum size is 20 mm, so we can directly make use of this. So now let's read this table. Ours is reinforced concrete and our exposure condition is severe. So under severe condition, what is the minimum cement content? 320. And what is the maximum maximum free water cement ratio as per this table? 0.45. Okay, please make a note of this. You please make a note of minimum cement content 320 kg per meter cube as well as 4.75. Sorry, 4.5. maximum free water cement ratio, which is coming from table 5. You please make a note of it. So now let's go to this mixed design. So that is actually written here. Whatever from table 5, maximum water cement ratio is given as 4.5. And please note that this trial and error, this mixed design is trial and error procedure. So sometimes after doing several mixed designs, you may use your experience. You may use your experience, understand? Here 4.5 is code is specifying, but based on experience, water cement ratio is assumed as 0.4. That is fine, okay? And you may say, I don't have experience, so what I should do? Then you go ahead and use 0.45, okay? Anyway, we'll make, once we do all the calculations, we need to do trial mixes, and then finally we need to arrive at the actual water cement ratio.
Sir, why 0.4, sir, with experience?
Hello?
Yes,
So now can you show them figure 1?
Figure 1?
Of 10262, figure 1.
Figure 1 is not the table 1, no?
No. You go to the original text and show the figure 1.
What figure 1? There is no figure here.
Now, go up.
I'm not understanding. What is the question? Hello?
Sir, why 0.4 with experience, sir? Why are we not going with 0.45?
I'm telling you here based on, because if you don't want it, you just go and take 0.45, okay? Instead of 0.4. And here it is the water content. Usually what is given in table 5? Table 5 is giving maximum water cement ratio, and you can adopt less than that. That is the ceiling. That is the ceiling of 0.45. So you cannot have water content more than that. So here, based on experience, it is. I'm telling you, please note that whoever worked out that illustrative example, he is saying, since this is given as maximum free water cement ratio, he is taking as 0.4. But if you say, no, I want to work out the calculation with 0.45, you can do it.
Professor Rao, do you have the 10262 2019 version?
This is 20. This is that only.
No, you are showing an old one. Can you show the 2019 version?
2019.
Yes.
No, 2009 only, last one.
No, okay, I'm mailing that to you.
Anyway, let's go through this, okay? So this 0.45 from IS 456 table 5 is the maximum free water cement ratio. You can even adopt less than that. So here it is, workout is shown for, or the details are shown, take it as 0.4. Okay. So now let's go to the next step, fifth step, selection of water content. So now we got water cement ratio, free water cement ratio, and table 2 of IS 10262. This current code is giving you maximum water content per cubic meter of concrete for nominal maximum size of aggregate. What is the nominal maximum size of aggregate? Our case, it is 20 mm. Ours is 20 mm nominal maximum size. And corresponding to that, what is the maximum water content? Or maximum water? It is 186 kg. Okay?
I have sent a mail. Can you please quickly check?
No, no, just let me complete. We'll
Okay.
see that. Okay. So for 20 mm nominal maximum size of aggregate, maximum water content is 186 kg. Okay. And but this table is based on certain assumptions. This table is for angular aggregates. This table is meant for angular aggregates and also slump varying from 25 to 50 mm slump. So if you agree with that, then you go ahead and take 186. Otherwise, you need to apply some corrections. What are those corrections? They are given here. Those corrections that you need to apply, they are given here. Let's go through this, okay? The quantity of maximum mixing water per volume of concrete may be determined from table 2. Water content in table 2 is for angular coarse aggregate and for slump 25 to 50 mm slump range. Is it clear? If your slump is different, if your aggregate are not angular, then what corrections? The water estimate in table 2 can be reduced by approximately 10 kg for subangular aggregates, 20 kg for gravel with some crushed particles, 25 kg for rounded gravel to produce same workability. So you need to see your aggregate, and depending on the type or the angularity and other things, you need to make these corrections. Is it clear? And what about slump correction? For desired workability other than 25 to 50 mm slump, required water content may be established by trial or an increase by about 3% for every additional 25 mm slump. So please note that in our example, what is this slump? What is this slump? Can somebody see and find it out? What is the slump we started with? Workability, we are aiming for 100 mm slump. Workability, we are aiming for 100 mm slump. So we need to apply correction. And what kind of correction? 3% for every additional 25 mm slump. Or alternatively, by use of chemical admixtures conforming to IS 103. So what we'll do is, first we'll apply this correction. At the end, we can make correction for these admixtures. Okay. So that is the way that is illustrated in this example. Okay. Anyway, time is running out. At least let's complete this and then we'll continue in tomorrow's class. It takes time, but with the whatever the explanation that I am giving, I suggest you need to open the code book and go through at least till the steps we covered. Okay. And let's complete reading this. This illustrates the need for trial batch testing of local materials as each aggregate source is different and can influence concrete properties differently. Water reducing admixtures or superplasticizing admixtures usually decrease water content by 5 to 10%. Here we are using superplasticizer. If you see the data that we noted, we are using superplasticizer conforming to IS 9103. So we need to apply some correction for that as well. And we'll see all those details at least by the end of tomorrow's class. Okay. And 20% and above respectively at appropriate dosages. Depending on the dosage of your superplasticizing admixture, you can reduce from 5 to 10% and 20%. Or 5 to 20%. So now coming back to this table 2. Table 2 is for angular aggregates. Our aggregate is angular aggregate, so no problem. No correction is required for that. But our slump is 100 mm slump, whereas this water content is within the range of slump from 25 to 50 mm. So we need to apply correction. What is the correction? 3%. 3% increase by 3% for every 25 mm slump. So our slump is 100, whereas this is valid for up to 50 mm. So balance 50 is left. So 225s. 225s in the sense 2 times 3, 6% additional water we need to add. So we'll see that and then we'll stop there. You can see here. From table 2, maximum water content is 186. There it is given as kg. Water density based on density, it's same as liters. Okay, 186 liters of water for a slump of 25 to 50 mm for 20 mm aggregate size. And now we need to apply correction, 6% additional. So 186 plus 6% multiplied by 186, so total 197 liters. And again, on the top of it, we are using super plasticizers. So this water content can be reduced up to 20%. Okay, so this 197 on that, you reduce it by 20%. 196 we arrived based on the slump requirement, but we are using super plasticizer, so you can reduce it 20%. 20% or above. Again, based on whoever worked out these details, based on his experience or based on the trials, he is saying instead of 20%, you can the water reduction can be up to 29%. Okay, based on trials with super plasticizers, water content reduction of 29% has been achieved. Hence, arrived water content is 197. If it is 20% reduction, 197 multiplied by 0.8 is the water content. But here he is saying 29% is taking. So 197 multiplied by 0.7. So this is the final water content. Okay. And we already noted above here, free water cement ratio is 0.45 maximum, and the details are worked out here with 0.4. So you got water content. You know what is the amount of water you are using. So you can calculate your cement. Water cement ratio is 0.4, and now cement content can be calculated. 140 liters of water and water cement ratio is 0.4, so you can back calculate what is the cement content. And now you need to compare the cement content that you got here with the minimum cement content that code IS 456 table 5 is specifying for severe condition. For reinforced concrete severe exposure condition, table 5 of IS 456 is specifying 320 kg per meter cube. So whereas here we got 350 kg. So it is fine. Suppose this value is less than 320, at least you need to use 320. Then you need to go back and work out your free water cement ratio and work out your water content. Is it clear? Please note that this is all trial and error. Here, luckily, our 350 is greater than 320 minimum cement content that is given in table 5. If that is not the case, we need to back calculate what is going to be the water cement ratio. Or we cannot do anything with water cement ratio because code is already putting a ceiling on water cement ratio. So using whatever cement content, we need to back calculate what is the using the cement content, minimum cement content, we need to back calculate what is the water content to keep the water cement ratio within the specified value given in the code. Okay, so we'll continue in tomorrow's class rest of the details like how to calculate volume of coarse aggregate, fine aggregate, and other things. But I suggest, actually I covered as slow as possible. Okay, but I suggest you please open your IS 10262 and then go through whatever explanation I have given and see if you have any questions. Okay. Any questions? Any questions, Professor Amlan?
would just recommend to use the latest version of 10262 because there it is more clearly written.
Okay, we'll see that.
See, some of the questions that you have asked will be clarified tomorrow.
Yeah, I will share with this. I will send this code, but there may not be much difference. Okay, there may not.
The solved problem is similar, but there are more explanatory sketches. Like in figure 1, it shows the selection of water to cement ratio based on the target strength. If the target strength is more, then the water to cement ratio is low. That is the conventional, what is called the Abrams model for making concrete.
Okay, I'm sending you the latest code. Okay, and we'll go through this code as well, and the old whatever 2009. Maybe you can work out your assignment based on both the codes. Any other questions, comments? Okay, then we'll meet tomorrow.